opportunity here, and we all have learned how to do these kinds of functions online. And therefore, as a result, this Alchemia is happening online. So I'm very happy and thankful to Xavier's Association of Chemistry for organizing this program. And I would like to wish all the participants, all the organizers, everyone, my best wishes to enjoy this 3 days of interaction with your peers, with people across the country, and learn something from these activities. Thank you, Ashmaji, for inviting me.
Thank you so much.
Thanks, sir.
Thank you so much, Principal Sir, for coming and gracing the inauguration ceremony. I now call upon our HOD, Marzban Sir, to speak a few words.
So first of all, many congratulations to ZAC as well as the Alchemia Fest for completing 18 years of its existence. ZAC was born in 2003, the first Alchemia Fest, though it was not called Alchemia, but it was in 2014. So we have completed 18 years. ZAC turns adult, even the Alchemia Fest. But I've always seen the fest as well as the ZAC committee or the ZAC Fest always going better from strength to strength. Every year we have done a better job. Okay, even in the pandemic years, we have managed it online very well. So congratulations to the entire organizing team, right from Charmaine to Pranav to Devina, Sayantan from the SY class. And special thanks to Ashma ma'am for coordinating this fantastic effort, where we start with conclave on the first day, then we have a plethora of events tomorrow and day after tomorrow. And as Principal Sir just said, that it definitely brings chemistry in a very different way to the students. It is learning beyond the classroom, and that is equally important for all of us, because ultimately when you jump into something, when you research something about it, then you learn more than just listening somewhere in a classroom. So I will request the ZAC team, the organizing team, to take over and make these 3 days very fruitful and enjoyable for all of us. And a warm welcome to even all the participants. Okay, ultimate enthusiasm for learning, which is more important from them. So thank you, one and all.
Thank you so much, sir. Those words are really encouraging, and I hope our events go on well. We now ask our participants and audience to wait for some time, as we will start the event by 2 p.m. Thank you so much. A very good afternoon, Rodney, sir. Thank you for coming. The event will begin in 2 minutes from now.
Hello everyone, a very good afternoon to you all. Today we have with us Professor Rodney Fernandez, Professor of Chemistry, IIT Bombay. He comes to us with an immense knowledge and experience of total synthesis of natural product and asymmetric catalysis with new methods of development of organic molecules. It is our great honor that we are able to host such an eminent scientist like Professor Rodney Fernandez. Those of you who have been associated with us in the past are familiar that Xavier's Association of Chemistry, or ZAC as we call it, is all student club. ZAC is run by the student and for the student. Of course, under the guidance of our faculty member of the Department of Chemistry, St. Xavier's College, Mumbai. We are a bunch of curious undergrads trying in our own way to popularize chemical sciences. For this session, there are a few simple rules I would expect everyone to abide by to make the session fruitful for all. Firstly, I would request everyone to keep their cameras and microphones off unless utterly necessary. If you have any question, please note them down somewhere. Do not interrupt the talk. At the end of the lecture, we shall have a question answer session. All the doubts pertaining to the talk are welcome. You can either type it down in the chat box or you may wish to use the raise hand feature of the Zoom to notify that you have a question. We will then ask you to unmute and ask your question. I would personally recommend everyone to clear the doubts in the Q&A session, as it is not that often that you get in touch with the very front runners in the field. Now I like to hand over to Sayantan to introduce Professor Ronnie Fernandez to the audience.
It is my great honor to introduce Professor Rodney Fernandez to our audience. Professor Rodney Fernandez finished his undergraduation from Dempe College of Arts and Science, Goa. Thereafter, he pursued his master's in chemistry from Goa University. He went on to pursue his PhD from the very prestigious National Chemical Laboratory in Pune. His quest for scientific exploration led him to Tohoku University in Japan as a postdoctoral fellow. He then moved to Institute for Chemistry, Organic Chemistry and Biochemistry at the Freiburg University in Germany, where he was the Alexander von Humboldt Fellow and DFG Fellow subsequently. Apart from his research background, Professor Fernandez started his teaching career right after his master's, halting only to pursue his higher education and come back and teach again. He has taught at Goa Engineering College, Institute of Chemistry at National Autonomous University of Mexico at Mexico City, Goa University, and Indian Institute of Technology, Bombay, where he is currently the Professor of Chemistry. Professor Fernandez has been awarded with many prestigious national and international awards and fellowships. A Young Scientist Medal, Alexander von Humboldt Fellowship, and Departmental Award for Excellence in Teaching at IIT Bombay, to name a few. He is also the life member of Maharashtra Academy of Sciences, Chemical Research Society of India, Indian Society of Chemists and Biologists, and Indian Association of Chemistry Teachers. He is also a member of many academic boards of IIT Bombay, Goa University, and MS University of Baroda. His work revolves on asymmetric synthesis of bioactive natural products, development of synthetic methodologies, and chemoenzymatic synthesis and asymmetric catalysis. I realize I've taken enough time already. Without further ado, let me hand over to Professor Rodney Fernandez. Over to you, sir.
Yeah, so just let me know if you can see the slides, okay?
Yes, sir. The slides are visible.
Slides are visible, right? You can hear me also, right?
Yes, sir. Very clearly.
Can you hear me? Yeah, so first of all, a very good thank you to Sayantam for the introduction. And I would also like to thank Sharmin Lobo for giving me the invite to come to this Alchemia of St. Xavier's College and to deliver a talk titled Total Synthesis of Natural Products, Asymmetric Catalysis and New Methods Development. Of course, it will be very difficult for me to cover a lot of work in this talk, but I'll try to give a glimpse of the kind of research that we do, and then finally wind up with the 3 short stories on how we develop new methods and 2 total synthesis. So in IIT Bombay, we work in 3 different areas. You can see on this slide. Total synthesis is very close to my heart, and I have been trained as a total synthesis person. I like doing total synthesis of natural products, starting from very simple molecules. You build up the molecule through stepwise and come to the final target molecule. The joy that you get when you make the final molecule and the spectral data matching with that reported in the literature, that is overwhelming. So we also develop new methods as and when we have, feel that some chemistry can be developed. And then many times when we work in this new method development area, we come a lot of serendipity. Okay? There is a lot of research goes in an entirely different direction. And then it is the presence of mind that and the interest that you have really makes a difference to understand the chemistry that goes and then explore it further. Now, asymmetric synthesis is another area that we work, which is a little tough because of an enantiomeric access that you need to get to really put it on paper as a attractive chemistry. So asymmetric synthesis and catalysis is definitely a tough area. So we connect all these 3 areas sometimes and then mix them well and come up with something interesting chemistry. So to show some glimpse of research initially before I go to the detailed talk, we have done some contribution in Wacker oxidation. Okay, I'm sure all of you know what is Wacker oxidation. It is terminal olefins being converted into methyl ketones. And in 2013, we had seen a paper by Professor M.G. Kulkarni from Pune University. He developed KBRO3 as an oxidant. Okay? And being an organic chemist at that time, we thought that why not use some of the oxidants that we use in organic chemistry to try out and see if they can work, okay, as a secondary oxidant in the Wacker oxidation. And the very first thing that came up in our mind was chromium trioxide. Okay? And this chromium trioxide molecule really works very well. You can see 42 examples we explored on all terminal olefins to give these methyl ketones. Now, when this work was completed and when we submitted this paper for publication, at least 5 journals rejected the paper. Not that the chemistry was not interesting, it was very interesting chemistry, just 0.5 equivalent of chromium trioxide was enough, but chromium trioxide was toxic. So that provoked us, okay, to understand that from the reviews which we got from the paper, that we have to walk beyond chromium trioxide because it is toxic. And then, of course, the work was published in Tetrahedron in this journal in 2014. And then we came up, okay, with iron sulfate. Okay, and we all know iron is already present in nature, and iron sulfate was a much mild Benning oxidant. Okay, and now you can see the work being accepted in ACS journal, okay, with 39 examples of terminal olefins converted into methyl ketones. We went ahead with another oxidant that is, we call it as hypervalent iodine oxidant. So hypervalent iodine is known for oxidation of alcohols to aldehydes or ketones. We used this Des-Martin periodinane. Okay? So this is also a very good oxidant, and palladium, okay, is the one which is required for catalysis. So this work was also very interesting to see that we could convert, almost like 61 examples, different substrates, terminal olefins were converted, okay, into methyl ketones. So since this work was important, we filed a process patent in 2015, and this process patent was granted in 2019, okay, on the process for development of Wacker oxidation by using Des-Martin periodinane. So method development is not just enough, but when you develop a method, you have to see that this method is also used by somebody, okay, so that it has a broader applicability. And we were quite astonished to see that our work being used by others. Okay, in 2016 or 17, okay, this work was used for this terminal olefin. Okay, at a crucial stage, at the last step, they used our chemistry that you can see Des-Martin periodinane and palladium acetate. This terminal olefin is converted into methyl ketone. And the authors say that among the large number of methods at our disposal, we choose the procedure recently published by Chowdhury and Fernandez. So that was quite nice to see that our chemistry he could use in this conversion. In fact, more papers came up. Okay, in 2018, another paper reported our chemistry of, you can see Des-Martin periodinane and palladium acetate for converting these terminal olefins into this ketone. Okay, and apart from that, a Hague-type reaction also occurred on the molecule. A professor from Goa University, Professor Santosh Tilve, okay, he used also our chemistry of using the IBX or using Des-Martin periodinane. He says Fernandez et al. Have revealed an operationally simple and scalable method to mimic the Wacker protocol. So he used it here to regioselectively functionalize these double bonds to the ketones. Okay, so that was quite nice to see that our chemistry was used for the synthesis of these piperidine alkaloids. We also developed another chemistry based on same Wacker oxidation that if we do it on allylic alcohols, okay, you can see these are homoallylic alcohols. You can oxidize this, okay, directed by this hydroxy, you get a ketone, and the hydroxy group gets eliminated to have these interesting beta gamma unsaturated compounds. When we were trying this Wacker oxidation, okay, on diene systems, okay, that is, you have 2 double bonds, we wanted to see where Wacker oxidation occurs, and we employed iron sulfate as the oxidant, and we found that there was no Wacker oxidation, but a regioselective cleavage, okay, of this terminal double bond, okay, only, not the internal, only the terminal double bond to give you an aldehyde or ketone. Okay, and here palladium catalysis was not required, iron sulfate was enough to do the regioselective cleavage. So you can convert terminal dienes, okay, into cinnamaldehyde type of compounds which have a lot of applications. So we recently reviewed our work for last 5 years in Wacker oxidation. We had done more than 10 papers in Wacker chemistry. So of course, we are still continuing a lot of work in Wacker chemistry. So we contributed a review article, okay, in catalysis technology in 2020. Okay. So one can read this paper, the recent developments, okay, in Wacker oxidation, including our own chemistry that we have developed. Coming to the asymmetric synthesis and catalysis, as I said, it's a very tough area to work with. We have developed pi-allyl palladium complexes. Okay, as you can see here, almost like 6 or 7 pi-allyl palladium complexes we prepared, and we used them in asymmetric allylation of imines to prepare this kind of chiral homoallyl amines. Now, what was known in the literature was Yamamoto catalysis, where he developed the same pinene catalyst, but he has a methyl group here, which is small group. We put an isobutyl group, and so the isobutyl group made wonders, because it could create the required steric hindrance so that this transition state is not favored. The reaction goes through this transition state, and you can see the jump from enantiomeric access 91% to up to 98% EE. So these complexes exist as dimeric complexes, okay, in the crystal structure, as you can see here, with 2 chloride breaches. So at that time, okay, we were wondering that why use only pinene skeleton, but we can also use, okay, the manthane skeleton. Of course, manthane was used as a chiral auxiliary, but not in catalysis. So we were first to show, okay, that manthane skeleton can also be used in catalysis. So the first work was published, okay, in 2012, and later on we thought that, okay, since these complexes exist as dimeric complexes, is it possible that if you keep a chain length between 2 such units, is it possible that such 2 units fold and have intramolecular dimerization depending upon this chain length? Okay, so we put some different chain length here and had 2 such units and prepared these complexes to see if this can dimerize, okay, intramolecularly, but this was not observed. And what we observed is that, okay, you have these 2 chains standing together and forming these chloride bridges, okay, over here like a ladder. Okay, so you can see 2 such molecules dimerize, okay, not intramolecular dimerization. And this we could prove, okay, through the crystal structure, okay, that is the X-ray structure, where we have taken, and you can see these are purple ones are palladium, these are green ones are the chloride bridges. Here is one more such chloride bridge, and these are the 2 units which stand together. Okay, this was remarkable. Okay, we did not expect this. We thought we would get something like this one. So these complexes can also be used in asymmetric allylation, and we could get an enantiomeric access up to 93:7 or enantiomer ratio. We have also developed pi-allyl palladium chemistry for leaving group ionization versus the allylic CH activation. You know, the pi-allyl palladium is very easy to form here, okay, when X is a leaving group by using palladium 0. But if you use palladium 2 in the catalysis, this allylic CH activation can take place. So what we observed, okay, as accidentally, that when we use palladium 0, you get allylic alkylation or arylation here, but when the palladium 0 is oxidized by air, it gives palladium 2, and palladium 2 cannot do further reaction here, but it activates this allylic hydrogen, and you can do double arylation. So that was very interesting chemistry, which we published in a very high-end journal of American Chemical Society, where double arylation was done. As you can see here, 1 arylation was done, 2nd arylation was done. Okay? And these compounds were very important for making them, okay, into highly functionalized and useful molecules. So that was, okay, asymmetric catalysis. I have a lot of work, but it's very difficult to present it in a short time. Okay, and one of the other area that we are working, okay, presently for the last 5-6 years, advocating, okay, to develop protecting group free synthesis. What do I mean by protecting group free synthesis? Okay, you see that because of chemoselectivity, when you have 2 functional groups, it's similar reactivity, and if you want to do reaction on one of the functional group, you have to mask the other functional group. You can use several of these masks. Okay, we call them as protecting groups. So you can see several protecting groups on the left side. I want to say no to protecting groups, because each protecting group requires 1 step to add, 1 step to remove. Okay, so 2 steps are added for each protecting group. If you have a 20-step synthesis with 5 protecting groups, 5 into 2, 10 steps will be added. So that is not a good strategy for step economy. And we have been advocating to see that can we do the synthesis, okay, by no protecting groups. And we have been quite successful, okay, and we have published 2 review articles recently on protecting group free synthesis, either through catalysis or through other approaches. Okay, you can read these papers available in 2020. We published 1 paper, and 2021 another paper. Okay, this is catalytic and protecting group free, and this is evolution of strategies in protecting group free synthesis. I'll show you some synthesis which we have done, okay, in remarkably short steps, okay, with chiral centers. Not only these molecules are, you know, just synthesized, but they are synthesized with the required chirality. So first molecule is a Hagan-Sklan electron, which we published in 2012. This molecule was synthesized in just 4 steps. Okay, earlier synthesis were as long as even 12 steps. Okay, which can bring down to just 4 steps. Okay, it is all the strategy that you have to use and no protecting groups. So D-gluconolactone in one pot manner was converted into this lactone, which you can see the part present over here. Okay? And so we had to add one side chain, and this furan ring we could install, okay, through iodocyclization. So just 4-step, one pot conversion to this lactone, cross metathesis, iodocyclization, deiodination. A protecting group free synthesis of 2 of the Hagan's-Klan lactones was available in just 4 steps. Now we filed a process patent for this because it was such a short strategy, and this patent was granted, okay, in 2018 on these 2 molecules. We have also developed a short synthesis for cardiobutanolide. Okay? You can see this molecule has 5 chiral centers, contiguous, 1, 2, 3, 4, and 5. And in stereochemistry, you know 2 raised to n. So that is 2 raised to 5 means 32 stereoisomers are possible for this compound. Okay? And we have to fix one of the stereoisomer with all these chiral centers as shown. Okay? And we develop, okay, just a 4-step strategy for making this molecule. So I have shown one pot synthesis of this one. And we did, okay, that way that you take this D-gluconolactone, commercially available cheap material, you treat with zinc powder, HBr, and acetic acid, and have this lactone prepared. Once you have this lactone, you can have this allyl alcohol prepared through Sharpless method, and you tie them together. That is cross metathesis.
Sir, you have been muted. Could you unmute? Uh, Sir, we can't hear you. I guess you have muted yourself.
Unmute. Yeah, so is it possible now to can hear?
Yes, sir. Yes, sir. You're audible now.
So I don't know how much I missed. Anyway, I just wanted to show how we have done protecting group free synthesis of this molecule cardiobutanolide with 5 chiral centers in a contiguous way. And since it is just a 3-step process, we could file a process patent on this molecule. Another compound that we have synthesized in a very short sequence of just 3 steps is this cephalosporolides. You can see the complexity in the molecules. It has pyro centers, 5-5-5 system, and you have to have all this chirality the way it is. So we took this commercially available epoxide and opened it up with allyl grignard to prepare this alcohol. And then L-mannonic lactone in a one-pot manner could be converted into this lactone. And now you do a cross metathesis between these two, you have this compound. Okay? Now see, the beauty of the synthesis is that we need a keto group here, okay, so that these 2 hydroxy can catalyze. And the keto group comes from the double bond. Okay? So we call this double bond as a masked form or latent keto functionality. And this can be observed, or this can be obtained through a Becker oxidation. We knew that this oxygen will direct, okay, the Becker oxidation at the right position that we wanted. Okay? So this hydroxyl group or this oxygen atom directs the Becker oxidation over here. And in having these 2 hydroxys, okay, at the right place in the 1,5 position, they go and catalyze with this ketone. And that's how this spirocyclic center comes over here, which is an acetal or a ketal. And since you get 2 of these stereoisomers, we could separate these 2 diastereomers. It's 60% one, 29% by column chromatography, and both of them are natural products. So a 3-step linear sequence, okay, of 22.8% and 10.5% overall yield, we could prepare this compound in a very short sequence, okay, and in an asymmetric synthesis way. So this was also granted patent in 2019. So we have prepared many molecules, okay, through the protecting group free synthesis, as I have shown here, and all of them are chiral molecules. It will be difficult for me to show synthesis of each of them. So
Excuse me, sir, just a minute. I think there is some network issue. We cannot hear you.
Sir, you're not audible. Maybe you can try joining back again if that works.
Sir, please unmute yourself. Hello, sir. Sir, we didn't listen you.
Ayushi, this message has reached, sir. You can, we all realize we cannot hear, sir. Your message has been conveyed. Thank you.
Can you enable my sharing?
Yes, sir. The sharing has been enabled.
Yeah, so let me go back. Can you see the screen?
Yes, sir. The screen's visible.
Yeah, so I don't know what was the issue.
Yes, sir. We were on this slide.
Okay, so so Wiley approached me if I can edit a book, and so this book was published in 2018 with forwards by Professor R.V. W. Hoffman from Germany and Professor G. Mehta. As I was explaining this picture that we have see on this book that was designed by me, in the sense that this number of pebbles over here represent the steps of synthesis. So if you have a 4 steps here and if you have a 9 steps here, the efficiency of the synthesis can be judged by the image, okay, in the water, okay, or the mirror, okay, in the water. So you can see that this is a downward slope. So as the number of steps increases, the efficiency decreases. Okay, so that means that you have to avoid protecting groups in synthesis so that you have step economy. Okay, well, so with that small background, I come to the actual part of talk. That is, I will show some 3 of my work over here, okay, which we have in details, okay, that we have done in organic synthesis. Okay, one of them is a methodology, while 2 of them, okay, 2 of them are total synthesis. Okay, so let me take first one, that is rearrangement of beta aryloxy acrylates. Okay, now this work came, okay, as a serendipitously discovered new reaction. We did not plan this. So let me show you how interesting it becomes in organic synthesis when you plan something on paper and something else get formed. Okay, so in 2012, okay, we saw a lot of work by Professor Delibes Sames, okay, from the US, that he was trying these hydride transfer reactions. What does it mean by hydride transfer? Okay, if you place a hydride, okay, at a sufficient place position, you will see that, and if you keep a pendant, okay, acceptor for the hydride, this hydrogen gets, or hydride gets transferred, okay, to this Michael acceptor. We call it as conjugate 1. So this hydride, once it is transferred, you get a cation here. The cation is stabilized by this oxygen lone pair. We call it as an oxocarbeniamine. So once you have an oxocarbeniamine, the enol that is formed here comes and cyclizes. Okay, as you can see in this work, when this hydride is transferred here, you have an enolate type compound formed here. and you have an oxocarbenium. Okay, so this enolate becomes a nucleophile, oxocarbenium becomes electrophile. Okay? And when this negative charge falls back, this double bond attacks over here, and oxygen gets back its lone pair. So you get beautifully this pyran type compound, or here the benzopyran compound. So when we saw a lot of work by Delibes, we put a question mark that can we have a system like this way, okay, where you have a benzylic hydride over here and you have a pendant enol which can accept this hydride. Okay, so we thought that if this hydrogen is transferred here, we will get a benzylic cation, and the benzylic cation will be stabilized by this benzene ring, and the enol that is formed here will come back and cyclize with this cation, and we will get this functionalized benzopyran. Okay, so this was the thought on paper, and when we went in the laboratory and did this reaction, you can see how faith emits in a different way. Okay, so we did not get this product, we obtained something like this way, and very good yield, 94% yield of this compound. Okay, so we did an analysis of this reaction. It can be observed that two of these aryl rings are present over here. Only one of this red marked thing is present here. Okay, so that tells us, okay, that some rearrangement has taken place. Okay, so we could assign this structure, and we went back by X-ray structure to confirm this reaction, and then you can see the X-ray structure proved that what structure we have put forward here is what we have obtained. We call it as an annulative partial dimerization. Okay, we call it partial dimerization because two such molecules dimerize, but two of these phenol moieties end up in the product. Only one of this ester moiety ends up in the product. Okay, so it's a partial dimerization reaction, but a beautiful reaction in the sense that we are making a complex molecule from a very simple one. Okay, and this is nothing but the 4-aryl dihydrocoumarin. This is a coumarin molecule. If you have a double bond here, we call it dihydrocoumarin, and it is 1, 2, 3, 4 position. You have another aryl group. Okay, so it is a 4-aryl dihydrocoumarin. Okay, and when we went into literature, we found several molecules which have this 4-aryl dihydrocoumarin moiety. You can see this is the coumarin moiety. You have 4 position, the aryl group. You have here also the same, here also the same, here all the same. So these are all natural products which have a such moiety. So this chemistry was very important. Okay. We also saw more molecules as can be seen in these slides, and some of these molecules have bioactivity. They are active against KB cell lines, which are cancer cell lines. We also observed, okay, that some of these compounds or 4-aryl dihydrocoumarins can be converted, okay, into drug molecules. For example, this molecule has been converted into tolterodine, okay, or it's also marketed as Detrol, which is an anti-muscarinic drug which is used for urinary inconsistency. So, our chemistry, okay, of making these molecules had some relevance, and you can see there are many other bioactive molecules which are known in the literature for such reactions. Okay, so that's why we took up this chemistry to understand what happens again, why we got such a rearrangement reaction. Okay, so we wanted to study first, okay, the mechanistic studies, okay, why this reaction went for a rearrangement. That is, two of such molecules end up into partial dimerization. The reaction was first optimized, okay, as I said before, with BF3 ethylate as a Lewis acid 0.5 equivalent in dichloroethane as a solvent, 80 degrees for 4 hours, it gives 94% yield of this molecule. So what was the observation here? The observation was that two such molecules of phenol are incorporated. That is, this beta blue structure is the phenol, and the red structure is the acrylate type group. Okay, so one molecule of the acrylate involved with one molecule is being lost. Okay, so you require two such molecules, but one molecule of the acrylate gets lost. So we did some study in the sense that we first wanted to prove, okay, that if one acrylate molecule gets lost, that this red mark gets lost between two molecules, then there should be a cleavage of this oxygen-carbon bond. And we had to prove that this carbon-oxygen bond breaks. Okay? And if that breaks, then we understood that phenol will be liberated. Okay? And if phenol gets liberated, then two different molecules, when we employ in the same reaction, we should get crossover products. So that tells us the reaction will be intermolecular reaction. So we took two different substrates here, as you can see, and the red part is the same, but the phenol part was different. In one case, we blocked these ortho positions because we did not wanted cyclization. Otherwise, okay, we will have 4 compounds. That is, one coming from these two mixture, other way mixing, and then self-dimerized compounds. So total 4. We wanted to avoid 4 compounds. We were knowing that we will get 3. Okay? That is, self-dimerization of this will give this product, cross-dimerization will give this one, and self-dimerization of this will give this one. And since the ortho positions are blocked, we cannot cyclize this compound. So these were the 3 compounds expected, and we went ahead, okay, to test whether there is a crossover product formed. Okay, and indeed we got in all the cases that we tried, 5 reactions we tried mixing different compounds. Over here you can see that all the cases we got a mixture of 3 compounds, and all these 3 could be separated by column chromatography, and we could even analyze them. Okay, and one case we even got the X-ray structure. So that tells us, okay, that the carbon-oxygen bond breaks. So we went further for trying to find out, okay, more proof for that. If the acrylate part is lost, okay, we tried to prepare a compound of this type, because acrylate is a small molecule, okay, which when gets lost, it's very difficult to identify. But if we have a naphthalene-like moiety, we'll be able to identify the acrylate part. So we prepared this ester with this naphthalene moiety, and when we did the Lewis acid mediated reaction, this part dimerized, okay, to give this product. The acrylate part went for cyclization, okay, like this way. So we thought that if the acrylate part goes into cyclization, let us prepare the acrylate part separately and subject it to the same reaction conditions. So we prepared this acrylate part separately and subjected to these conditions. We got the same product, okay, which we obtained here. So that tells us that this acrylate is actually lost in this reaction. We also prepared another molecule to show that this red bond is the one which is cleaved. You can see we blocked all the ortho positions as well as the para positions so that there will be no dimerization. And indeed, when we did the reaction, there was no dimerization. Okay? Because now all positions are blocked for dimerization. We see this oxygen carbon bond breaking, quantitative recovery of phenol, 35% we could recover this ester. Some of this ester gets hydrolyzed and we could get this alcohol. Okay, so that proved beyond that, you know, this oxygen carbon bond breaks. We also did deuterium labeling studies by putting deuterium, okay, at 2 places. One at this terminal position here and one at this internal position here. We could incorporate D1, okay, 84% in the molecule, D2 78%. And when we subjected this di-deuterated compound for this reaction, and when we analyzed the deuterium present, we found that D1 was intact, okay, from 84 to 80 is intact, whereas D2 was lost, 78 to 18%. That shows in the reaction, D2 should be involved, okay, or the hydrogen that was present here should be involved. So in that way, okay, doing these experiments, we came up with a reasonable mechanism, which was quite accepted. Okay, now you see how the reaction occurs. 2 such molecules are involved. And as I said, one of the molecule loses acrylate. So one of these molecule, when it complexes with BF3 etherate, it gives us this oxocarbenium ion. Okay? So this becomes the electrophile. And now when the other molecule complexes with boron trifluoride, it cleaves this oxygen carbon bond, generating this acrylate and a phenolate. You know, this phenolate becomes a nucleophile, and this undergoes a electrophilic substitution reaction on this electrophile to give us this compound. Now this has the oxygen carbon bond, so it undergoes, okay, a intramolecular oxygen to carbon migration, okay? And you have this kind of carbon-carbon bond formed. And now this is an enolate, okay? So the enolate can tautomerize to the keto form, okay? And that is the reason, okay, that this reaction is reversible. And that's why the hydrogen or the deuterium present here was lost, okay, because it is reversible reaction. And once you have this free hydroxy, it cyclizes with this ester to form this lactone, okay. And so this is how the dimerization occurs with loss of one of this acrylate molecule. Now to prove that, okay, this is an intermediate, we prepared this compound separately, okay. So you can see this compound was prepared and then subjected to the same conditions to check whether this OC bond breaks and a carbon-carbon bond forms. And indeed, we got the same product, okay? So that proves that this is an intermediate in this reaction, and it undergoes an O to C migration reaction. So this was a reasonable mechanism for the reaction. So we went ahead, okay, to optimize, after optimizing the reaction to see its substrate scope, you can see large number of molecules we could prepare by changing different functional groups on the aryl rings. We could dimerize and get this product. We have even the halogens are tolerated, okay, iodo, bromo, chloro were tolerated, and so on. Okay. The only difficulty in this reaction, as I said before, it involves an electrophilic substitution reaction. So the benzene ring should be electron rich. And if you have electron withdrawing group, the reaction cannot take place because you cannot do electrophilic substitution on aromatic ring which has electron withdrawing group. So in these cases, the reaction failed. If you block the ortho positions, then there is no cyclization occurring because this para-hydroxy cannot cyclize with this ester. In that case, we got only these dimerized, uncyclized compounds. As I said before, okay, that this chemistry has a lot of applications. So we went on to prepare, okay, a lot of analog molecules for bioactivity studies, and we prepared several tolterodine analog. Okay, this is a drug molecule, so we can see we have prepared around 13 compounds, okay, which have analogs of tolterodine, but we could not take up the bioactivity study for want of expertise and the available facilities for bioactivity study. Only thing we could do is antibacterial study. We have also prepared the GPR40 agonist. We have prepared ROR-SA inhibitors and so on. And all these compounds, we took them up for antibacterial studies over 5 different strains. This work was done in CDRI, that is Central Drug Research Institute in Lucknow, where we sent our samples and they analyzed the samples against these 4 bacterial strains. And one of the molecule turned out to be quite good. It was active at a level of 1 microgram per ml. So we want to bring this concentration still down, and we are doing structure activity relationship, and we have prepared 5 more compounds with a substituted aryl ring over here, and those will be soon submitted for bioactivity studies to see if they can give much better activity than these present ones. So that was the methodology part, that is the, as I showed, one part, as new method development. As I said before, it was a serendipitously discovered reaction, and we explored it in a large scale, for making several analogs and compounds. Now, the next topic that I'm going to take is the total synthesis of asterisquinolide C molecule, because total synthesis is very important. How we build a molecule in the laboratory, starting from very simple compounds. The very first step in total synthesis is choice of a molecule. So we did some literature, and we found that there were a series of compounds isolated in literature in 1982. So these were 4 such molecules, and you can see they differ in only the double bond geometry. Here you have cis-cis, here you have cis-trans, you have trans-cis, and all these are trans. So they are named as asterisquinolide A, B, C, and D. They were again isolated in 2001 along with other molecules. And from 1982, nobody touched these molecules for synthesis. So in 2013, we took up the synthesis part of these molecules. And when we started the synthesis, there were no synthesis reported on these compounds. But as we went ahead, 6 months into the synthesis, the first synthesis came up. So that became, that made us our synthesis as a second synthesis. But nevertheless, whatever synthesis came in the literature was an asterisquinolide D. What we synthesized was a C. Now, these compounds are very good anti-cancer compounds. You can see 4 cancer cell lines, these compounds were tested and compared with a cisplatin, which is an anti-cancer molecule or a drug that is used. Cisplatin requires IC50 of 8 micromolar, whereas this compound you can see 8 times much more potent, 1 micromolar. So that's why the synthesis of this molecule was important. And so we took up the synthesis. At that time, as I said, for 3 decades, 1982 to 2012, these molecules were not touched for synthesis. In 2012, beginning of 2012, we took up the synthesis of these molecules. The major challenge in the synthesis of these molecules is a strained 11-membered ring, which has to accommodate 3 double bonds. That makes the synthesis more challenging. And I can show you in literature how people have struggled to make 11-membered rings. You can see these double bonds were tried to be closed by Kojima. He could not get an 11-membered ring. He got simple dimerization of this molecule to an acyclic dimer. Now this terminal bond is more reactive, it just dimerizes. It does not close with this one. So then another molecule, what he tried is that he removed the double bonds, and he thought now it should cyclize. You have only 2 double bonds which should go and cyclize. He got a cis compound, and in around 65% yield. Now you can understand that in order to make only 1 double bond in an 11-membered ring, it is so difficult. You have to prepare 3 double bonds in this ring. So that was the challenge. One of the important development that we observed in 2012 when Hamata tried to ring close this molecule here to make budeldone, that is this trans double bond here, which in this is 11-membered compound with 2 double bonds. He was trying to ring close here. He did not get this molecule. He got again a linear dimer. So what we observed, and what trick he used, sometimes organic chemistry requires some tricks. You can see here this ketocarbonyl. This carbon is an sp2 carbon, which has a bond angle of 120 degrees. He understood that probably this bond angle prevents these 2 ends to come closer. So he made a temporary cyanohydrine. And now this carbon is sp3, and so it is 109 degree bond angle. So you reduce from 120 to 109. Now these 2 ends come closer, and you can do a ring closing metathesis. And in situ, you can remove this cyanohydrine to get back the keto. So this is very important when it comes to making such rings. But of course, as I go in the synthesis, even this trick failed in our case. So when we select a molecule, the first thing we do is a retrosynthesis. Okay, we try to see where to cleave the molecule and come up with the simpler structures. Okay, and since this is a lactone, we thought that we can make this bond by esterification. This double bond we planned to ring closing metathesis. This double bond we planned again to ring closing metathesis. And since now this is an ester, we have one side as an alcohol, the other side as an acid. Okay, so one fragment is alcohol, the other fragment is an acid. Okay, so I'm not going to show the synthesis of these two fragments. Believe me that they were synthesized in 5 to 6 steps. I'll directly go for the coupling stage that these two fragments, alcohol and the ester, were coupled, okay, to form this ester over here by Yamaguchi esterification. And now we were at a stage, okay, to try out a very promising double ring closure. Okay, that is, these two will close here, these two will close here to give this molecule. But when we subjected it to the ring closing metathesis condition by using Grubbs to catalyst, only this 5-membered ring closed. Okay, here this did not close. Maybe that this is a highly strained system and getting this two and closer was not possible. We tried to further subject this compound to a repeated ring closure, but we got very low yields. 2 to 5%, okay, and that too they were not pure compounds, okay, because of this olefin geometry. So what we thought, okay, is to mimic the Hamata's strategy. That is, we saw one ketone present here, okay, and we thought that can we reduce this bond angles over here from 120 to the sp3, okay, that is 109. So we took a alcohol here and tried to see if we can reclose. Okay, now also even after having an alcohol, only this 5-membered ring closes, this does not close. Okay, even after subjecting it to this, we got very low yields. So 2 of our strategies failed here. Okay, so then we did a revisit and thought that we can try, okay, not the metathesis conditions, but we should try the Wittig reactions. Okay, that is the Horner-Wittig. If we use this, okay, phosphonate and this aldehyde, we may be able to do a Horner-Wittig reaction. Okay? And so that can place either a trans double bond or a cis double bond. And again, since this is an ester, we went back to our original ester and then identified one fragment as an acid, the other fragment as an alcohol. Okay? So we prepared those 2 fragments. I don't show the synthesis. And then we coupled these 2 fragments for esterification. We got this one. We did a ring closing metathesis over here. We have this 5-membered ring formed, and now we have to close over here. The protecting group was removed to get the alcohol, and now this alcohol was oxidized with des-Martin pyridinane to the aldehyde. And now we have this phosphonate and the aldehyde for Wittig reaction. We tried 3 different conditions here, but none of them could close, okay, over here to get this molecule. Again, you can understand that, an 11-member ring formation is very difficult. Okay, so we went into literature to see, okay, if such chemistry has been explored. Kodama tried, okay, for example, 11-member ring formation by Horner-Wittig. He did not get this. He got only 3%, which is so low yield, okay, of this double bond. What he got is a dimerization, 22-membered ring. Okay, 2 such molecules remain in the opposite direction and they cyclize to get this molecule because this is an 11-membered ring. Marshall had tried, okay, this kind of chemistry with an alkyne here, which gives a linear structure, but here he was successful and it is a 12-membered ring, okay, with 1 double bond, 1 alkyne. Okay, so this gave us some idea, okay, that how we can solve our problem, okay, in the synthesis. So what we were trying to do, okay, is we were trying to close over here to make an 11-membered ring. But if we open up here, you can see 1, 2, 3 carbons. If you go this side, we have 1, 2, 3, 4 carbons, okay, or 4 atoms. And so now if instead of closing here, if we try to close this end first, we are going to make a 12-membered ring, okay, that is this one. And once this is ready, we know that these 2 are very close. Okay, so we can now contract it from a 12-membered to a 11-membered ring. So this is a simple trick we thought on paper and went back to the lab and tried it out. Okay, so you can see that this ester was there with us. And so we took it up and then tried, okay, instead of closing here, we tried to close this side first. Okay, so this TBS group was removed. We have an hydroxy here. We have a phosphonate here. This hydroxy was oxidized by des-Martin pyridinate to the aldehyde. And now we did a Wittig reaction here, or a Horner-Wittig reaction. Now we got the ring closure. These are 12-membered rings. We got a mixture of cis and the trans compound in a 1:1 ratio. We could not separate this compound. So we took them up as a mixture for the next step of contracting from 12 to 11-membered ring. That is, these 2 ends has to be closed. Okay? And when we tried this reaction, okay, it worked well. Okay, you can see that the ring closure occurs, okay, with Grubbs, different catalysts, Grubbs 1, Grubbs 2, and Grubbs 2 in 15 mole percent, 90% yield. Okay, now one thing that we observed, okay, that is these 2 compounds which could not be separated, The trans compound over here does not cyclize and it gets decomposed in the reaction. Only the cis compound cyclizes. Okay? So that can be understood because trans double bond, okay, in an 11-membered ring is very difficult. Cis can be accommodated. So we could complete the total synthesis of this molecule, okay, by going from a very simple strategy of 12-membered to the 11-membered ring. Okay? So you can see how total synthesis becomes difficult, and at times we have to use certain strategies and work out and finally end up getting what you want. Okay? So coming to the final part, okay, a short synthesis, another 6 slides. I will show a short synthesis of another molecule over here, which is a very sensitive tri-wine natural product. Okay? You can see when these molecules were isolated in 2013, 8 compounds were isolated, and the structures were given based on NMR data, and they proposed, okay, the natural product to have a trans stereochemistry. When the first synthesis of this molecule was done, it was proved that this stereochemistry is not trans but cis. Okay, so total synthesis sometimes also helps, okay, to correct the structures. Okay, when people give structures, you find that sometimes stereochemistry is wrongly assigned. Okay? So the first synthesis of this molecule, which has at the head, okay, a butyrolactone and 3 alkyne, very sensitive 3 alkynes in conjugated form, it was done by Mohapatra, okay, from Indian Institute of Chemical Technology, Hyderabad, IICT. He used D-mannitol as the chiral pool material, required 8 steps to convert this into this molecule, another 4 steps to prepare this alkyne, and another 3 steps to reach to the target molecule. So a total of 15 steps were required for him, okay, to synthesize this in 2017. When we saw this paper, okay, we thought that we can cut down the steps from 15 steps, okay, to only 7 to 8 steps. So we designed a strategy in such a way that this bond we want to make to Cadiot-Chodowicz coupling, and then this alkyne compound we can prepare in just 3 steps from this lactone. And as I showed you before, this lactone can be prepared in just 1 pot, 2 steps, okay, from this compound. Okay, so based on this strategy, we went ahead. You can see the synthesis. We started from L-mannonic lactone. In a 1 pot, 2 steps procedure, we could convert this lactone into this one. Okay? And this stereochemistry is cis. Now this hydroxy would interfere, so we protected this as a TBS ether. And now this terminal double bond, we knew that this oxygen would direct Becker oxidation at this position, and we should get an aldehyde. And the moment you have aldehyde, we installed this alkyne. 2 procedures were known in the literature. One is called as a Corey procedure, that is this CBr4 butyl lithium, and the other one is called the Bestman-O'Hara reagent. Now the Corey procedure did not work because you are using very harsh butyl lithium conditions, and this lactone does not survive. So we adopted, okay, these Bestman-O'Hara conditions, but we could get only 42% yield. There is another precursor to Bestman-O'Hara called as the Seifert-Gilbert, and this we could use, okay, and we could get 55% yield of this alkyne compound. And once we have that alkyne compound, we went for the synthesis of the other fragment, and that was prepared in quite short way, okay, by doing, okay, a Glaser-Hay coupling to get this compound. PMS group was deprotected with potassium carbonate. We have this bis alkyne, and we needed a bromine here that was introduced with NBS. So this was the fragment ready. This fragment, we took it here for a Cadiot-Chodowicz coupling. It is nothing but an alkyne-alkyne coupling. So these two could be coupled to have this tri-wine. Okay? And then this TBS group was removed with HCl that completed the synthesis of this molecule. This is light sensitive molecule. So we had to do a rapid column chromatography to purify this compound. So since it has 2 chiral centers, we thought that we should synthesize all the 4 possible stereoisomers. 2 chiral centers mean 2 raised to 2 equals to 4. Okay. So we prepared SS. This is the natural product. We wanted to also prepare the trans compound. Okay. And the trans compound we could prepare by isomerization of one of the chiral center. You can see that this is allylic center. We could palladium catalysis. We could isomerize this from alpha to the beta. And now this is trans. Okay. And repeat the same steps. We could prepare this trans compound. Now to make the enantiomers of this compound, we started from D-gluconolactone. And this could be converted, okay, into this enantiomer, and then this can be taken to the cis compound, which is RR enantiomer to this molecule. And if we isomerize this compound, we have the other molecule also. Okay, so you can see here now all the 4 molecules were prepared, or 4 dimestereomers were prepared. Okay, and so this was the actual natural product, okay, which has this configuration. Now this was a 7 to 8 step synthesis. We went for another strategy that we thought that can we bring it down to just 4 steps. Okay, but the strategy was very simple. Okay, we knew that these 2 hydroxyl are cis placed. Okay, so if we have a double bond here, we can dihydroxylate this double bond. One of the hydroxy will go and cyclize with here to make this. The other hydroxy will remain here. So we needed to prepare this compound. Okay, and you can see in 1 step we can go here one coupling gives the molecule. So 2 steps, okay, from this we can prepare the compound. Okay? And you can see the short synthesis which was achieved without any protecting groups, okay, involved. Okay? We have this commercially available compound. This alcohol was oxidized by Swan oxidation to the aldehyde. We did a modified Knoevenagel reaction with half ester of malonic acid and prepared this beta gamma unsaturated ester. Now this can be subjected to Sharpless dihydroxylation by using 2 different ligands. If you use DHQ ligand, you get alpha-alpha stereochemistry. If you use DHQD ligand, you get beta-beta stereochemistry. Both these enantiomers were prepared in a very good enantiomeric excess of 93%, 94%. And now 1 Cadiot-Chodowiecki coupling, we could prepare these compounds. We actually claimed in the synthesis that this whole synthesis can be run in only 3 days. And you can see no protecting group involved, and the synthesis is so efficient that you can prepare in just 4 steps. Now you can understand, okay, the power of organic synthesis, that Mohapatra synthesized this molecule in 15 steps, we synthesized in 7 steps, and finally to catalytic approach, we made these molecules in just 4 steps. Well, so with that, I want to show some NMR spectra of these compounds, how once the molecule is synthesized, we compare it, and we understand that we have made the target molecules. Mohapatra prepared this molecule and published in the literature with this spectra. We call it the proton NMR spectra. You can see the peak by peak matching of this. This peak matches over here. This doublet here matches over here. This bunch of peaks matches here. You have 4 bunch of peaks which are also over here. Okay, this is the proton NMR. We have carbon 13 NMR. You can see the carbon 13 NMR also perfectly matches. This is taken in acetone D6. So we have a acetone D6 solvent peak here, which we can see over here. This peak is matching here. These 2 peaks are matching here. You can see that all these peaks, even these 2 closely packed peaks are matching here. This peak is of the ester, okay, carbonyl. This ester carbonyl, this is matching over here. This is acetone carbonyl, okay, which is present here. So peak by peak, it matches. And that is how we confirm, okay, that what we have synthesized is the target molecule. So to summarize, okay, my talk, I have shown, okay, a lot of work that we have done in new method development, asymmetric catalysis, asymmetric synthesis, as well as total synthesis. Okay, so I have shown one rearrangement reaction that we found serendipitously that this kind of molecules dimerize to get this. We prepared drug molecules like tolterodine GPR40 agonist, ROR inhibitors. I have shown, okay, total synthesis of acetylquinolide C. We got some challenges there, and we used a simple tricks from 12-membered to 11-membered ring for synthesis. We showed you, okay, a highly sensitive tri-wine natural product by bringing down the steps from 15 to 7, and then finally to catalytic approach, only 4 steps. So well, okay, organic synthesis, okay, or our endeavor in organic synthesis is a lot of challenges. Okay, we had a lot of challenges. What I have shown synthesis are those. They're still the easier one. There are many syntheses which we had to fight for 2 years, okay, sometimes. So definitely organic synthesis has challenges, failures, and triumphs. It is like a joy ride, okay. Sometimes you are very high, sometimes you come down where there are failures, sometimes you have success, you go up, come down, come up, come down, okay. So that's what how organic synthesis is performed in the laboratory, okay. I thank all my group students, okay, who are very enthusiastic in doing organic synthesis, which is very tough. Total synthesis nowadays people don't want to do because it is very tough. But some of the enthusiastic students from my group have been able to take up the challenges and do total synthesis. We not only work in the laboratory, we also have fun outside the laboratory. My research group RAF, one of the students, my first student Chauhan, coined this word, okay, as research and fun group. Okay, RAF is research and fun group. Definitely, research is definitely fun. Okay, when we do it, okay, with a lot of interest and so on. Well, I thank all my students. The work that I have shown, okay, was done by Sachin, who is now a postdoc in Israel. Rupesh, okay, who is now an assistant professor in Goa University. Praveen has done some work. He is going to join in another 2 days Jubilant Pharmaceuticals in Delhi. And Ram Krishna, okay, has done some work. He has submitted his thesis and he's a postdoc in my laboratory now. 14 students have graduated with their PhD degree. Right now, I have 16 students and 2 postdoctoral students. There are many others who have worked as project staff, master students, intern students, and so on. Okay, I thank them all. I also thank, okay, the funding agencies, because a lot of these funds that were required in total synthesis came from DST, BRNS, CSIR, INSA, and the Humboldt Foundation. Well, I want to show a small video which my student prepared, and I hope that I have another 4 minutes which you can grant me. Now, in a total synthesis, you can see these are the steps involved, okay? That is selection of a molecule. We do retrosynthesis on paper, and then we take this paper-based synthesis to execute in the bench, okay? So we have to do a reaction setup. we have to do column purification, and then we have to do NMR analysis. And these 3 steps, okay, has to be repeated, okay, to every step of the synthesis till you reach the target molecule. Okay, so I will unshare this, and then I will go to share a small video in another 4 minutes. If you can spare me, my student has prepared this. So I'll show that.
Of course, sir, you can go ahead, share the video.
Yeah, so I'll show a small video which my student prepared. I hope it is it visible? I don't think it is visible. So let me share it again, the screen.
Yes, sir. Maybe you can try sharing the entire screen.
Yeah, so can you see the video?
Yes, sir.
Yeah, so this is Priyanka, who is going to show how we set up reactions in the laboratory. You can see a flask here, which she is showing over here. She uses this flask, it's a 2-neck flask, and we use a balloon here because this balloon is filled with argon or nitrogen, because we have to maintain sometimes dry reaction conditions. We don't require interference of oxygen or air. Okay, so we use this balloon after flushing this reaction flask. Now she has added solvent and the chemicals or reagents that are required. It's a 2-neck flask so that we can add sometimes reagents that are required. Okay, and so she takes it up now for stirring. You can see it is stirring on this magnetic stirrer, which is developed from Hedolf. And if you want to add reagents, you don't have to open this flask. We put a septa here, and with the help of a syringe needle, she adds the reagent to this reaction vessel. So you can add multiple reagents to the reaction vessel in the liquid form. Okay, if you want solid form, we have also solid form apparatus that we can add in a solid form. Okay, now this is stirred for a reaction time, whatever, and then we do after the reaction is over, we try to monitor the reaction. And if the reaction requires heating, you have a hot plate here, we can put this oil bath. Okay, now sometimes reactions are to be done at very low temperature. Okay, ice can give up to 0 degrees or -5 degrees if we mix ice and salt. This is called julabo, which can go up to -90 degrees. Okay, so if somebody has set up a reaction at -48 degrees at a very low temperature, it can give cold bites. Okay, so this has ethanol here, which can be taken up as a solvent, and then you have a circulator here which chills the solvent, okay, through the circulator, and this can cool temperature up to -78 degrees. So once the reaction is done, we do a TLC, that we call as a thin layer chromatography, to judge whether the reaction is complete or not. Okay, you can see the TLC how she is showing. This is the starting material on the left side, and the right side you can see that spot corresponding is not there. A new spot comes up. Okay, so that is tells us that the reaction is complete. Okay, so once the reaction is complete, we have to work up the reaction. Okay, because there are many inorganic impurities present. So we do an aqueous work she has done in dichloromethane. So she takes it up for separation of these 2 layers. So she puts up, okay, into a separating funnel. Now in the separating funnel, you have to stir, not stir, you have to shake it. And once you shake it, you can see the 2 layers, okay, getting separated. Okay, you can see this. The down layer is a dichloromethane layer, which is more denser. The top layer is water. Okay, so you can separate these 2 layers by you opening this, okay, down cork here, and then you collect this the solvent into a flask. And this flask is now taken up for concentration. So you will get a crude compound. Okay, so this is a rotary evaporator of Buki from Switzerland, costing around 6 lakhs. You can remove this solvent, which goes into this condenser and falls into this collection flask. And so you can concentrate it. Once you concentrate it, you have the crude compound. The crude compound is taken for column purification. And so she will show how a column is loaded over here for purification. Which is by gravity, we do this column. So you load it with silica gel, and then you load your compound on the silica gel and collect the fractions. Okay? Once you collect the fractions, you again do the thin layer chromatography and see where you can see on the spots that we had shown before. And once those spots are eluted, you again concentrate those fractions which has the compound. And once the compound, okay, is obtained as a pure compound, you can see here sometimes it is 10 to 20 milligrams. It could be even 1 kilogram. So we do a small scale reactions, and now this Ashwin is doing, okay, a kind of a sample preparation for the NMR study. He is adding CDCl3 here, deuterated solvent, to this, and then with the help of a pipette, he is going to take it up in an NMR tube, and that NMR tube he has to load it in the NMR machine. You can see this is a thin tube over here, in which he is putting the sample. It is around 1.5 inches. You have to show the sample over here, and that you have to take it up for the NMR measurements. Okay? So we have a very costing around 3 to 4 crores instrument, that is a 400 megahertz NMR instrument. This has auto sampler. You can place all your NMR tubes here. It automatically picks up the samples and loads it into this magnet. And then you come back, okay, to a screen here where you do all the analysis, feeding up of the data. And then, you get the FID file from here and you transfer the FID file through your email and come back to the office where you work or the laboratory, and there you process the NMR. And I have already shown you, okay, the NMR, which I had H1 NMR as well as the carbon-13 NMR, okay. So the whole process of organic synthesis involves selection of the compound, retrosynthesis, going to the laboratory, bench scale execution, right from setting up the reactions to workup of the reactions to column chromatographic purification, and then analysis. So this is a lot of work, okay, when you do total synthesis. And if any step fails, then you have to again go back, again repeat, change strategies, and so on. Okay. So with that, I wind up here, and I thank the organizers for giving me this opportunity for giving this talk. And if you have any further questions, I would be happy to take up any questions. Thank you very much.
Thank you, sir. That was a really insightful talk, and especially the mini lab tour that you gave through the video. That was really wonderful. I personally enjoyed it very much. Because we are already over time, we'll just take the questions which we have received earlier via our email. Sir, the first question is, like you showed that you use CrO3 for Wacker's oxidation, and then you use Fe2SO4 whole thrice. But the number of products that you obtained were different. In CrO3, there were 42, and in Fe2SO4 whole thrice, there were 39. So why is there a difference in the number of products that were?
No. I think you have not understood it. It is not different products that are obtained. It is a single product reaction. See, if you have this R group, for example, if I show it on the screen, if you see this R group is say pH group, okay, and a benzene ring, okay, it will give only one product. Okay? These are different examples that we have done. Okay, so these 42 examples that we have done, okay, with different R group here. You can see here methyl ketone, methyl ketone, methyl ketone. This group is different. Okay, so it is not that in one reaction you get several products. In one reaction you get only one product. We have analyzed different substrates. Okay, maybe 49 or 42 substrates were screened by using chromium trioxide. Whereas here we have 39 substrates, different substrates where R group differs. Okay, and so here we have 61 examples where 61 different substrates were tried. Okay, like you can take say styrene compound, you can take substituted aryl compound. So each compound is different. Okay, and so everyone has this terminal double bond, and that will give you only one product. Okay, not that in this reaction you get 61 products. Okay, it is 61 different examples that were executed.
Okay, thank you, sir. I hope that answered the question. Sir, the second question is, in the paper that you showed of Kodama in 1987, it showed the formation of a 22-member ring over an 11-member ring. So what is the reason that the 11-member ring is so difficult to form?
See, when you form a ring, okay, it is not difficult to form a ring which does not have double bonds. Okay, but if there is a double bond, you know that if you take a trans double bond, for example, okay, the trans double bond has bond angles of 120. That means a trans double bond takes, okay, away the two bonds. Okay, if you see, for example, this one, okay, you can see this bond moves away, this bond moves away. Okay, so if I put another trans double bond again further away, okay, but if you have cis double bond, these bonds are brought closer. Okay, so it is easier to prepare a compound with a ring compound with cis double bonds rather than trans. You can see every bond which you put takes the ring away. Okay, from here. Okay, here it is trans, here it is trans. Okay, so this kind of molecules, when you have three double bonds, they take the bonds away, okay, rather than bringing them together. And that is the reason why, okay, Kodama must have suffered. Okay, you can see, okay, you will be able to see here there is one trans double bond. This you forget, okay, and you are trying to close over here with one trans double bond, taking this bond and this bond away, bringing these two bonds closer is difficult. Okay, and that's why. And then, okay, this is a disubstituted double bond. This is a terminal double bond. So it is very easy to dimerize a terminal double bond. That's why you get dimerization here. Okay. Similarly, you can see in that case over the other one, okay, where you got a 22-membered ring. Okay, I don't think where it is. Okay, I think it is later on. Yeah, here. Okay, here also you can see three double bonds are present trans. This is trans. This is trans. This is trans. And every trans double bond takes the bonds away. Okay, and that's why these two such molecules lie parallel to each other. And this one, okay, aldehyde condenses with the phosphonate of the other molecule. The phosphonate of this condenses with the aldehyde of the other molecule, and you get this. So the bigger the ring, it is easier to accommodate trans double bonds. And that's why he was getting this 22-membered rather than this one.
We'll just take one last question. Sir, a question has come which says that since we already know the bond strengths of all the bonds in the molecules, why is it that we fail to predict which bonds will break and some other bonds end up breaking?
No, you are talking in the context of which molecule?
So
In the
that
method.
hasn't been mentioned. It just says that why do certain bonds tend to break unexpectedly?
It is not unexpectedly, okay, because it depends on the reagents that you use, okay. See, if you want, for example, in this case, okay, if you want to break a benzene bond, okay, here, there are oxidants which can break this benzene bond, okay. If you use, say, ruthenium chloride, okay, it oxidizes these benzene bonds, okay. So certain bonds will break depending upon the conditions that you use, okay. For example, when I use BF3 etherate, it's a Lewis acid, okay. So Lewis acid goes and coordinates. Lewis acid is an electron acceptor, okay. So it goes and coordinates with oxygen. For example, it has lone pairs, okay. And so when this lone pairs, okay, react with BF3 etherate, it coordinates here, okay. And when it coordinates here, this pi bond has to break, okay, because it has to form a bond with that. When this pi bond breaks, the next pi bond moves here, okay. When next pi bond moves, you will get a cation here. Now oxygen has lone pairs, okay. So that lone pair stabilizes, okay, that cation, okay. And that is what I showed, okay, in the mechanism, okay, of the reaction. So it is which bonds should break depends upon the reagents that you employ, okay. See, for example, if you employ, okay, ozone, okay, as an oxidant, it will cleave the double bond, okay. If you employ lithium hydroxide, okay, it will hydrolyze the ester, okay. So because it's a basic condition. So depending upon the reagents, you know, okay, that which bonds will cleave, okay. It's not just like that the bonds will cleave, okay. You have to use particular reagents to break particular bonds.
Okay, sir. For any further questions, can we share your email address with the audience?
Yeah, it is RFERNAND, R Fernand.
Yes, sir. We'll share it with them on their email addresses.
Yeah, sure.
We'll now like to conclude our event. I would like to call Charmaine Lobo, our chairperson of ZAC, to deliver the vote of thanks.
A very good afternoon to the audience and our speaker for today, Mr. Rodney Fernandez. I'm honored to deliver the vote of thanks on behalf of the entire team of ZAC. I want to thank our guest speaker, Professor Rodney Fernandez, for accepting a humble invitation and enlightening our students with latest research available in the domain. I have no words to offer gratitude for your valuable presence, sir. I'm pretty sure the insights gained from today's talk will surely encourage some of our audience to delve deeper into the area. I would also want to thank our head of department, Mr. Marzuban Kotwal, and our convener of ZAC, Dr. Ashma Agarwal, for supporting us at each step. A big thanks to Team ZAC who helped the event run seamlessly. But most of all, thank you to our audience for being highly cooperative, and it is because of you we keep going. I would hereby rest my speech. Thank you so much, sir, once again.
Yeah, thank you very much and goodbye.
Thank you, sir.